Right. Good afternoon, everybody, and good morning. So today we are very glad to have Elliot Marshal from School of Mathematics in Monash University, and he's going to talk about this very exciting topic, unstable fluids in expanding cosmologies. So thank you, Elliot, for agreeing to speak at this seminar, and please take it away.
Thank you very much. It's really nice to be invited to speak here, and thank you for changing your regular seminar time for me so that I didn't have to speak at 3 a.m. in Australia. So primarily what I want to talk about today is some work from my PhD thesis, which broadly covers the topic of relativistic fluids and expanding cosmologies. In particular, what I want to talk about specifically is some numerical work that I've been doing, which looks at certain types of instabilities which can happen in fluids in these cosmologies. So just to begin, as a sort of refresher, I just want to recall the Friedmann-Lemaitre-Robertson-Walker solution, so the FLRW solution, which is an exact solution to the Einstein equations discovered in the early 20s by Alexander Friedmann. So this is really the basis of all modern cosmology. And it has a few features that are very nice. So it's spatially homogeneous and isotropic. So physically, we can think of this as there's no preferred direction, and our matter is evenly distributed. It has a few features that we would now consider common in modern cosmology. So it starts with a Big Bang and it isotropically expands to the future. And in this talk, I'm just going to be considering the simplest case, which is looking at flat spatial slices with a T3 topology. So this is the most commonly studied FLRW model, but also because we're looking at numerics, T3 is also the easiest situation to work with because we just have a simple periodic boundary condition. Okay, so ultimately I want to look at perturbations of these FLRW models, but in particular we can further classify them. So I said these are expanding models, and our expansion is determined by this function A of t, which we call the scale factor. And we can classify how fast our model is expanding by looking at the second derivative of these quantities. So we're going to say our model has accelerated expansion if the second derivative is positive, linear if it's zero, decelerated expansion if it's negative. And in this talk, I'm primarily focused on two cases, the sort of more extreme cases. So accelerated expansion and decelerated expansion. And as we'll see, these two models have very different types of properties when we start looking at nonlinear perturbations. Okay, so that's the general goal. I want to perturb FLRW solutions. But to make things a little more concrete, I want to emphasize the specific system I'm working with. So of course, I'm looking at the Einstein equations coupled to the relativistic Euler equations for a perfect fluid. I'll also be including a cosmological constant at some points. So this term lambda is either going to be a positive constant or zero, depending on whether I'm looking at accelerated or decelerated expansion. And I said I'm coupling to a perfect fluid. So my stress energy tensor has this form down here. So P is my pressure, rho is my energy density, and V is my fluid for velocity. Now, to close this system of equations, we also need what's called an equation of state. So that's relating the pressure to the density of my fluid. And in this talk, I'm just going to consider the absolute simplest case, which is a linear equation of state. P equals K times rho. And here K is the square of my fluid sound speed. So I'll be restricting K between 0 and 1. So there are physical and mathematical reasons for this restriction. So K equals 1 is when the fluid speed is the speed of light. So it's natural to assume that our fluid shouldn't have a sound speed greater than that. And then outside of this region 0 to 1, there have been questions about the well-positiveness of the Euler equations. So this is a natural restriction to make, and indeed, it's the most commonly studied case. Additionally, I should also mention that our fluid velocity has to be time-like and normalized. So its norm is going to be -1 with respect to our metric. Okay, so we're looking at the Einstein-Euler system, and really the main goal of my research and the main goal of this talk, hopefully, is to study the future stability of expanding FLRW models. So ultimately, I'm interested in asking this question. If I take a small perturbation of FLRW initial data, does my perturbed solution exist globally to the future and remain close in some appropriate sense to FLRW? Now, in this talk, I'm of course looking at cases where we don't remain close to FLRW because I'm interested in instability. Okay, so that was a very brief background of what I'm trying to do. We're looking at perturbed FLRW models in the Einstein-Euler system. So as I said, there are two cases that I'm interested in. So the first is accelerated expansion. So in some sense, this is the more physically reasonable case. We expect, based on observational evidence, that our own universe has accelerated expansion, but it's also the more mathematically tractable case. So this is where the majority of rigorous results have been established. So it's natural to first look at in this situation. Okay, so I said I'm interested in perturbing these FLRW solutions, but more generally, we can just look at perturbations of homogeneous cosmologies. So spatially homogeneous cosmologies are the simplest case because the field equations just reduce to a system of coupled ODEs in this case. So it's much more amenable to analysis. And there's two specific classes of homogeneous spacetimes that I'm interested in. So the first I've already introduced, the FLRW spacetimes, which are spatially homogeneous and spatially isotropic. But we can also consider a slightly wider class called the Bianchi spacetimes. So these are spatially homogeneous, but in general anisotropic. And they get their name from this classification of 3D Lie groups, the so-called Bianchi classification. Now, I should mention that, strictly speaking, FLRW can be interpreted as just a special case of these Bianchi spacetimes. But in this talk, I'm going to distinguish between the two. So when I say FLRW, I mean homogeneous and isotropic. And when I say Bianchi, I specifically mean anisotropic spacetime, so not the FLRW case. Okay, so we're interested in perturbing these simple spatially homogeneous solutions. Now, other than the fact that the field equations become ODEs, spatially homogeneous spacetimes are nice because they have a lot of additional structure. And in particular, we have a preferred foliation of our manifold. And this gives us a natural way of classifying fluids in these spacetimes. So we can call a fluid orthogonal if its fall velocity is aligned with the normal vector of my foliation, and we can call it tilted otherwise. And the reason you want to introduce this distinction is that orthogonal and tilted fluids can have very different asymptotic behaviors towards the future, or indeed the past. So it's natural to introduce this distinction. Now, to make things a little clear, like what do I mean that they have different asymptotic behavior, I just want to consider a simple motivating example. So let's consider a fluid on a fixed de Sitter background. So I'm not coupling the fluid to the gravitational field yet. I'm just looking at a fluid evolving on de Sitter. And I'm going to be evolving towards the future. So if my fluid is initially orthogonal, then it remains orthogonal. So it's a fixed point of the homogeneous system. And this is true for all values of my sound speed parameter k. However, if my fluid has initial tilt, then its asymptotic behavior is heavily dependent on what my value of the sound speed is, what is k. So for k between 0 and 1/3, these tilted fluids become orthogonal asymptotically. So the tilt dies out at future time like infinity. At k equals 1/3, so this is a special case called the radiation fluid, then if my fluid has non-zero tilt initially, it keeps this non-zero tilt. On the other hand, for k larger than 1/3, we get a very different type of behavior, what's called asymptotic extreme tilt. So this is where the fluid approaches a null vector at future time like infinity, and the components of the fluid fall velocity are coming unbounded as we approach future time like infinity. So the key takeaway that I want to emphasize here is that k equals 1/3, the radiation fluid, acts as a bifurcation point between two very different types of behaviors. For k less than 1/3, we have asymptotically orthogonal fluids, and for k greater than 1/3, we have this asymptotic extreme tilt. And it's important to introduce this because, as it turns out, this will be crucial to looking at nonlinear stability of these FLRW and homogeneous spacetimes. Okay, so that's a little idea of the difference between orthogonal and tilted fluids and why we want to introduce that distinction. But more generally, let's just consider the expected behavior for accelerated expanding spacetime. So let's just consider solutions to the Einstein equations with a positive cosmological constant and arbitrary matter. So in general, there should be some restrictions on the matter, but I won't get into that in this talk. Okay, so it turns out we have a really strong heuristic picture about what should happen here. We expect that these spacetimes should approach a homogeneous and isotropic end state, so the de Sitter solution, at late times. And we also expect that the matter should, in some sense, become negligible at late times. So this is really called the cosmic no-here conjecture, which was developed by Gibbons and Hawking and Hawking and Moss, respectively. And then it was actually rigorously proven by Wald in the restricted case of the Bianchi spacetime, so asymptotic isotropization and convergence to the de Sitter solution. And more recently, there have been a wide range of rigorous stability results which support this picture. So we really do have this strong idea that space-time expansion should smooth things out. We should approach a homogeneous isotropic end state, and matter shouldn't play so much of a role at the late times in the universe. Okay, so that gives you a sort of general expectation of what should happen when we have this accelerated expansion. But I want to emphasize that the results I've sort of mentioned or discussed up to this point are really about homogeneous spacetimes. But of course, our own universe is not homogeneous. We have inhomogeneous structures. So in fact, we have to start looking at perturbations of these solutions to really have some idea about how they behave in general. So now I just want to give a brief rundown on some key results for the stability of FLRW solutions with positive cosmological constant and linear equation of state. So the key result for us really is due to Rodniansky and Speck. So they proved the first stability result in this regime, which is stability between dust and radiation, so K between 0 and 1/3. And subsequently, these endpoints were also proven, so K equals 1/3 and K equals 0. So these results that I've listed just here refer to the T3 flat FLRW solution, but you can also prove equivalent results outside of T3. So for example, the work of Mondal shows this. But the key point that I want to emphasize here is that all these results consider K up to 1/3. But already at the homogeneous level, we know that K equals 1/3 is this bifurcation point. So we get these two dramatically different types of behaviors: asymptotically orthogonal fluids for K less than 1/3, and asymptotically extremely tilted fluids for K greater than 1/3. So the natural question to ask is, what happens when you start perturbing fluids with super-radiative equations of state, so K larger than 1/3? And that's what I've been primarily focusing on in my PhD research. So to begin, I just want to give a brief run through of the sort of known results and some of the expected results for these super-radiative spacetimes. So I'm going to split it into two cases. So we're looking at perturbations of our FLRW solution. So this is our orthogonal fluid solution. And then also perturbations of these tilted spacetimes, these Bianchi spacetimes. And I've also split the equation of state parameter into two cases. So K between 1/3 and 1 and K equals 1. So K equals 1 is called a stiff fluid, and it behaves in general quite differently. So I've separated that case to make that distinction clear. So the first result, to my knowledge, in this case, is looking at perturbations of FLRW solutions with a stiff fluid. And Greg Forner-Davlos actually proved that these solutions are unstable. And what he actually shows is that you get this extreme tilt behavior in finite time. So the fluid velocity becomes a null vector in finite time, and then you can't continue your solution as a fluid anymore because your fluid velocity has to be time-like. So then the natural next question is, well, what happens in these Bianchi spacetimes in the stiff fluid case? And it turns out there you also expect this instability to happen, this extreme tilt and finite time instability. But to my knowledge, there are no rigorous results right now. The reason you expect the same instability is because already at the homogeneous level for the stiff fluid, you see this extreme tilt and finite time sort of instability. So there's no real reason to expect that taking nonlinear perturbations would fix this or improve things. So I think the expectation is that it should be unstable. Okay, but that's the stiff fluid, which, as I said, is somewhat of a special case. So then the next thing to look at is, what about these spacetimes with K between 1/3 and 1? Now, if we perturb these tilted Bianchi spacetimes, it turns out we can actually get global existence and stability results. So in particular, in collaboration with Greg Fornadopoulos and Todd Oliynyk, we have two stability results. One is currently being written up, which proves stability for K between a third and up to 5/7. So only for a partial range, but we do get some sort of stability result. Now, I don't want to emphasize these results too much. I just wanted to mention them to show that you can actually get some sort of global stability result beyond this radiation threshold. But really, the focus of this talk, and in some sense, the more physically relevant case, is looking at these perturbations of the FLRW solution. And here you expect them to be unstable. And this is primarily due to a conjecture of Alan Rendall from about 20 years ago. So that's what I'll discuss now. What is Rendall's instability conjecture? So what Rendall was looking at was formal series expansions of the Einstein equations with positive cosmological constant at a future time like infinity. And what he found is that if the spatial fluid velocity vanished, at some point these expansions became inconsistent. So he conjectured that this was due to some sort of instability. In particular, he conjectured that if we consider nonlinear perturbations of the FLRW solution to the Einstein-Euler equations, for which the spatial velocity vanishes at some point at future time like infinity, then the density will develop large inhomogeneous features, and this quantity called the density gradient will blow up as we approach future time like infinity. So the density gradient is this quantity here. It's the spatial derivative of the density divided by the density. Okay, so that's a lot to take in. But the first thing is, well, in what sense is this an instability? Well, on a spatially homogeneous spacetime or an FLRW spacetime, this quantity, the density gradient, has to be zero. So if this quantity is blowing up or becoming arbitrarily large, in some sense, we're becoming arbitrarily far away from our background. And moreover, we're actually developing large inhomogeneous features in the density, which is not what you would expect in a stable spacetime. Okay, but more importantly, arguably, is that if this conjecture is true, it totally differs with that expected behavior of expanding cosmologies. So you'll remember we have this expectation that our models should approach a homogeneous and isotropic end state, and the matter should in some sense become negligible. But what we're seeing here is that the matter would actually become extremely inhomogeneous and anisotropic. So we're in a totally different regime. So this would be a counterexample to that cosmic no here picture. So in that sense, it's interesting to determine, when does this conjecture actually hold? Okay, so the first way you would want to study this is just by looking at perturbations of these orthogonal fluid solutions on a fixed background. That's the simplest case. So just the Euler equations, not coupling to the gravitational field, just looking at a de Sitter background. And that's what we've done. And in fact, you can observe this density gradient blow up numerically looking at the T2 symmetric Euler equations. So this was done in a paper with myself in collaboration with Todd Oliynyk. And more recently, Todd has actually given a rigorous proof of this conjecture for the T2 symmetric Euler equations, subject to certain restrictions on the equation of state and the regularity, which I won't go into. But of course, these results don't truly answer Rendall's conjecture, which looks at the Einstein-Euler system. So the simplest way to study this, at least numerically, is to start looking at Gaudy symmetry. So this is joint work with Florian Beyer and Todd Oliynyk. So now I just want to give a brief rundown of our numerical implementation and sort of highlight a few of the key results before I explain what actually causes this instability. So we're going to be looking at what are called compactified T3 Gaudy metrics. So these are a specific type of symmetry class which are being used in a whole bunch of numerical and analytic investigations. But in particular, we're looking at metrics of this form. So they're compactified because we've compactified our time coordinates. So it ranges between 0 and 1, and tau equals 0 is going to be future time like infinity. So we're evolving in the direction of decreasing tau in these coordinates. It's a T3 metric. Once again, we're just going to have periodic boundary conditions in space. And it's a Gaudy metric, so it's a certain type of symmetry class, which I won't go into the details of here. But suffice it to say, we're going to be solving for our metric functions, eta, u, alpha, and a. They're only going to depend on tau and theta is going to be a 2 pi periodic coordinate on the 1 torus. So really, the key takeaway that I want you to have is that by going to this Gaudy symmetry, we end up with a 1+1 problem with periodic boundary conditions. And by compactifying our time coordinate, we've got a finite time domain to evolve over. Now, whether you need to do that, in general, I don't think you do. So the reason we compactified our time coordinate was to have a sort of synergy with the Fuchsian approach for proving global existence instability, but subsequent work we've done doesn't use this compactification, and you can get similar results. So I think it's not necessary to do this to get the same sort of numerical results. Okay, so Gaudy symmetry reduces the field equations to a 1+1 problem with periodic boundary conditions, but it also places some restrictions on the matter. So in particular, spatial fluid velocity can only have one non-zero component. So our fluid velocity has a v0 and a v1, and that's it. So not only does Gaudy symmetry simplify the Einstein equations, but it also simplifies the fluid equations in the sort of maximal way. And additionally, we also have a preferred gauge choice. So we're working in the areal gauge, which is where our time coordinate is proportional to the area of the symmetry orbit. Now, it turns out this is actually a really nice gauge to work in. So there are a lot of strong analytic results working with this gauge. So the existence of global foliations and all that sort of thing. But what that really says to us is that it's a nice gauge for numerics. You don't expect sort of any gauge issues to crop up when doing simulations. So that's why it's a natural first step to work in these sort of Gaudy spacetimes. Okay, so that was a sort of brief outline of how we're reducing the problem numerically. But now I want to discuss, some of the results we're actually seeing. So the first question is, well, do you see this density gradient instability? What actually happens? And here I've got a short animation which shows the density gradient instability. So this is for an Einstein-Euler perturbation of FLRW. And what you'll see is we form these sharp spikes, and this quantity is actually starting to blow up as we approach future time like infinity. So in particular, this is almost exactly what Rendall conjectured. So he conjectured you'd get these sort of spike-like features and you'd get this blow up of the density gradient. So really, numerically at least, it appears that Rendall's conjecture is more or less spot on. And just out of interest, on the next slide, I have a little animation which shows this instability in 2 dimensions. So this is just looking at a fluid on a fixed acidic background, but now in 2 dimensions, and we're looking at the norm of the density gradient. And what you can see is that the same instability happens, but now we can form these sort of cool inhomogeneous structures. So I really like this simulation, not only because I think it looks cool, but it has this sort of end result which is vaguely similar to the filament type structures that we observe in our own universe. So a natural question would be, if we gave our simulation some sort of physically relevant initial data, whatever that means, would this instability lead to some sort of nonlinear structure formation, which we observe in our own universe? So I don't know if it would, but it's interesting to think about. Okay, so really what I'm trying to emphasize here is that this density gradient instability happens. Rendall's conjecture appears to be, true, at least in terms of what happens. But then the question is, well, what actually causes it? What is the sort of mechanism for this instability? And it really comes down to the behavior of fluids on homogeneous spacetimes. So homogeneous fluids on fixed homogeneous spacetimes. And it turns out that Rendall's instability is really caused by the difference in behavior of tilted and orthogonal homogeneous solutions. So what we observe is that at late times, our fluid basically behaves like a homogeneous fluid, and at some points in our domain, it behaves like a tilted fluid, and at some points it behaves like an orthogonal fluid. So the way we can test this numerically is we can derive the homogeneous growth rates for the density, for example, and then we can compare our numerical solution to these growth rates. So if I look at an individual point in my domain, does it eventually start growing like one of these tilted or orthogonal solutions? So that's exactly what we've done. So here I've got a plot, and blue is our numerical solution at one point in my domain, so a fixed grid point. Will have some sort of tilt. And then in orange, this is the homogeneous tilted growth rate that you get from the homogeneous equations. And what you see very quickly is that our numerical solution rapidly approaches this homogeneous growth rate. So that really suggests that our numerical solution at late times is being dominated by this tilted ODE behavior. And you can do a similar thing with these near orthogonal points. So I'm saying near orthogonal because, of course, in a numerical simulation, the chance of hitting an exactly orthogonal point, which is where the spatial fluid velocity vanishes, is almost zero. The chance of having a discrete grid point exactly at that point is very low. But you can look at points which are very, very close to orthogonal. So the tilt is, 10 to the minus 13, 10 to the minus 14. And what we see at these points is that they behave very closely to the orthogonal growth rate at late times. So what this suggests is that the instability we're observing in this density gradient is really caused by the difference in behavior of two ODE solutions. So we have one point which is orthogonal and adjacent point which is tilted, and the density at these 2 points is growing at two different rates, and that's responsible for these spikes in that density gradient quantity. So it's really to do with homogeneous behavior. And just to sort of emphasize this point a little more, we could also look at the fluid velocity. So we can rescale our fluid velocity so that our equilibrium points, our extreme tilt equilibrium points correspond to v equals plus and minus 1, and our orthogonal points correspond to v equals 0. So our claim is that my solution will asymptote to one of these extreme tilt points somewhere in the domain, and in between it will cross to this orthogonal point. So we should expect this fluid velocity is going to approach some sort of step function. And in fact, you can see that. So if we look at this rescaled quantity and we evolve it, what we see is that our solution very quickly approaches this step-like quantity. So in one part of the domain, we're approaching this v equals plus 1 extreme tilt. Another part we're approaching is v equals minus 1 extreme tilt. And in between, we're crossing through this orthogonal solution. So really, that confirms that this instability is due to this ODE behavior, which is the dominant feature at late times. Okay, so that was looking at accelerated spacetimes. And in particular, what have we shown? Well, we've seen that we have numerical evidence for this Rendall instability, at least in the restricted case of Gaudi symmetry. And in particular, this instability is really caused by the fluid approaching these different types of tilted solutions. Now, from a more physical point of view, why are these solutions interesting? Well, they're counterexample to the expected behavior of these expanding cosmologies. So they're a counterexample to this cosmic no here conjecture. Okay, so that was the first thing I wanted to look at. So perturbations of these accelerated FLRW models. But the other case that I want to look at, which is in some sense the more sort of difficult case, is these decelerated spacetimes. So sometimes we'll call these slowly expanding models. So it's only recently that people have started to get rigorous results in this case and sort of numerically start looking at this. And in particular, it's because in this spacetime, or in these spacetimes, you often expect shocks to form, which is, of course, much more difficult to deal with analytically. So to give the sort of motivation for what we will expect to happen here, I have a little simulation here, which just shows a fluid evolving in Minkowski space. And what we see is very quickly we start to form shocks, discontinuities in our numerical domain. And in fact, we know this has to happen. So there's a well-known result of Christodoulou, which says that shocks have to form in finite time on Minkowski space. Okay, so this is looking at spacetimes with no expansion, which in some sense is the extreme version of decelerated expansion. But what about looking at expanding spacetimes? Well, here we know that shock formation can actually be suppressed by spacetime expansion. So the first result in this direction was in the Newtonian setting by Brouwer, Rendall, and Ruler. And then that Rodniansky spec result that I mentioned before is the sort of relativistic generalization. So what Rodniansky and spec show is that you get global existence for suitably small perturbations of this accelerated expanding model. So in particular, that shows that you don't get shock formation. So this is a process called fluid stabilization, in which the space-time expansion is somehow suppressing the sort of worst behavior of the fluid. Okay, but now what I've set up here is we've got the two sort of extreme examples. On one end, we have Minkowski space where we know shocks have to form. And on the other end, we have these accelerated expanding models where for suitably small perturbations, shocks don't form. So then the natural question to ask is, well, how much expansion is needed? At what point will shocks form, even if you have expansion in your solution? So that's the question that I've been working on more recently. Okay. So to begin in this direction, I really want to emphasize some key past results, and these are really due to the work of David Feynman and collaborators. So they've done a mixture of numerical and analytical work looking at fluids on fixed power law backgrounds. And there they find a transition between where they get stability results and where you get shock formation on these fluids. So in particular, they're looking at spacetimes of this form. So it's an FLRW type spacetime, and their scale factor quantity is this power law, T to the 2a. So they have decelerated expansion when a is less than 1. So that's the case that we're first interested in. And I should mention that their results are both available on arXiv right now. So what did they find? Well, Feynman and collaborators looked at fluids on these fixed background spacetimes, so K between 0 and 1/3, and they found that dust fluids are unstable for A less than or equal to half, stable otherwise. Barotropic fluids, so K greater than 0 fluids, are unstable when A is less than 2/3. And then for expansion, for our expansion parameter A between 2/3 and 1, this Ka parameter space is split along a critical line. So that's all quite a lot to take in, and it's not very clear, what that means just reading text. So on the next slide, I've actually got an image of this behavior that Feynman and collaborators have established. So on the bottom of my plot, my x-axis, this is the expansion rate in that T to the 2a quantity, and on my y-axis, this is our sound speed parameter K. My red region is where shocks form from arbitrarily small perturbations, and my green region is where they can prove rigorous nonlinear stability results. So they get global existence in some sense. And the black line here is this bifurcation point that they found between these two different types of behaviors. Okay, and I've added an extra line in this diagram in blue, and this blue line is exactly the FLRW solutions to the Einstein-Euler system with 0 cosmological constant. So it's looking at the decelerated FLRW solutions. So what we see is that from this, if we generalize this heuristic picture of a fluid on a fixed background, we see that we would probably expect that the FLRW solution is going to be unstable because it lies totally within this unstable regime, except at the dust case. So at dust, the FLRW solution is in this stable regime predicted by Feynman and collaborators. So that's the natural question to ask. Well, what actually happens when you couple to the Einstein equations? So that's what I wanted to look at, perturbations of the decelerated FLRW solution to the Einstein-Euler equation. And this is the numerical results here are written in a recent paper, which is available on arXiv. And I suppose the title, in some sense, kind of gives away what happens, which is that shocks form. Okay. So now I just want to give a brief rundown of the sort of setup of this problem. So as I said, Feynman and collaborators had numerical results, but their numerical scheme couldn't evolve shocks. So they used a pseudo-spectral scheme, which is not well suited to discontinuities and shocks. However, they do provide very convincing evidence that shocks will imminently form. So while they don't actually show that a shock forms, their evidence is very convincing that it is imminently about to. But a natural improvement of this sort of approach would be to use a shock capturing method. So this is a numerical method which lets us, resolve shocks in the domain. So not only can we, evolve up to the point of shock formation, but we can evolve past and model the interaction of shock waves in our domain. So the specific scheme I'm using is very generic and it's very easy to use. It's this Kurganov-Tadmor scheme. So it has a semi-discrete formulation and it's second order accurate. smooth solutions at least. In these shock capturing methods, you can't expect better than approximately first order accuracy at the discontinuities. And the first thing that I did was go back to that fixed background case and just try and see if we could replicate the results of Feynman and collaborators using the shock capturing method. And we can. So we do observe this bifurcation between stable fluids and unstable fluids on these fixed power law backgrounds. So that's the setup we're using for the fluid. But the next thing we have to look at is, of course, the Einstein equations. So once again, we're just going to do this in Gaudy-Euler. It's the sort of natural first step to studying these problems numerically. And we're implementing a flux conservative form of the Einstein equation. Now, whether that's necessary is unclear, but it does mean that it's using this flux conservative formulation makes it easier to apply shock capturing methods to the Einstein equations if we would like. And in particular, I should mention that the way we formulate the Gaudy-Euler system here is very similar to that of to the work of Laflock and collaborators. So they studied low regularity Gaudy-Euler spacetimes. So they were looking at weak solutions. They came up with a particularly nice formulation to study that problem. So we've slightly modified it for our purposes, but it seems like it's a naturally suited way to look at these shock forming problems. And as I mentioned, we've used both this Kurganov-Tadmor shock capturing scheme and finite difference methods to discretize the gravitational equations. And as I'll discuss in a little bit, it turns out that one method is preferred in certain regimes over the other. Okay, so that's the setup. We're looking at Gaudy-Euler equations again, but this time we're implementing shock capturing methods to deal with the fluid. Okay, so as one sort of last step before I start talking about the results, the natural question is, well, how do you actually know if a shock is formed in your numerical solution? And this is something that often isn't discussed in numerical papers. So if we use this shock capturing method and we have suitably high resolution for our scheme, it's often very obvious that a shock is formed. You can just see from visual inspection of your plots that it's discontinuous. But you would probably like some sort of more rigorous way of confirming what you can see visually. So we've considered two different ways. So the first is used in the work of Feynman and collaborators, and it's what we also use in our paper. So we check a norm of derivatives. So at a discontinuity in our numerical solution, if we approximate the derivative, we should expect it, or the norm of the derivative, we should expect it should blow up as our solution becomes discontinuous. So by monitoring the size of some sort of appropriate norm ratio, we have an indication of how discontinuous our solution is becoming. So a similar idea, which I played around with, is to look at mathematical entropy functions. So this comes more from the sort of conservation law side of things. So an entropy function is something which should satisfy a conservation law on smooth solutions, but then should increase when we have discontinuities. So the natural entropy for the barotropic or the linear equation of state, Euler equations, is the particle number. So this is an entropy for the relativistic Euler equations. And essentially what you would do is very similar. You would check something like the integral in space of your entropy function, and you should see that either it'll be conserved up to some numerical level or it won't be conserved if there's a shock. But primarily we've worked with this norm of derivatives approach. So just to make that comment about how you measure these things a little bit more clear, it turns out that these quantities, either the entropy function or these norms, are resolution dependent. So if I just say that a shock forms when this quantity is larger than 10 to the 4, say, then I won't actually be confident that I'm actually finding a shock for a fixed resolution. So to make this clear, here I plotted this norm ratio for a solution which does form a shock at around t equals 10 for 5 different resolutions. And what you see is that this quantity actually becomes larger depending on how sharply you're resolving this discontinuity. So the main point I want to make is that it's not enough to just choose some fixed number and say, if this quantity becomes larger than that number, a shock is formed. You really have to keep in mind is that a numerical approximation is really interpreted as a sequence of solutions. So we actually have to look at the sequence to be confident, qualitatively that there is a discontinuity that is being more sharply resolved, which is leading to this norm quantity, blowing up. Yeah, so that's a rough idea of the sort of numerical strategy we're using to confirm what we can visually see very clearly. Okay, so now I want to go through some of the key results. So to begin, I just want to start looking at fluids with K greater than 0. So remember already from Feynman and collaborators' results, the dust case K equals 0 behaves differently than these barotropic fluids, as they call them. So for sound speeds K between 0 and 1, not including 0, and initial data suitably close to FLRW, we observe highly oscillatory shocks form in the fluid variables. We observe highly oscillatory behavior in the metric, and then we also observe that the shock formation time decreases exponentially as the size of both my perturbation and my sound speed are increased. So that's a lot of text, but maybe it's more obvious if I show some animations. So here I'm plotting the fluid velocity in a case where we have shock formation, which is all these cases, I should say, have shock formation. So what you see is we have this sort of rapid side-to-side oscillation in our solution, and very quickly you can see that we have these sort of sharp discontinuities forming in the fluid. So as I said, it's quite obvious from visual inspection that it's formed, once it has formed. Okay, so we always observe shock formation for these K greater than 0 fluids. And then the next thing we can do is, well, what about the metric function? And so the metric functions also have this sort of rapid oscillation, which it is decaying in some sense, but we always observe some sort of oscillatory behavior. And in particular, I want to emphasize that the metric functions always appear to be smooth. We don't see any sort of discontinuities forming in the metric, which is what you would expect. Okay, so we see shocks in the fluid and we see oscillations in both the fluid and the metric. So then the next question you'd want to ask is, well, what about this Rendall instability? So in the work of Feynman and collaborators, they didn't consider K greater than 1/3, but we have in this paper. And what we find, well, if you first looked at the spatially homogeneous equations on a decelerated background, you might expect that you would see this Rendall instability because this tilt bifurcation still occurs. You have extreme tilt for K greater than 1/3 and orthogonal for K less than 1/3. But what we find numerically is that our perturbed solutions are never reaching this ODE dominated regime. So the ODE features are never the dominant, force in our solutions. And so we never observe this Rendall instability. And in some sense, I think this is not surprising. So this seems to be consistent with the known stability results for linear and decelerated fluids, where they have some sort of quantity which never quite decays, which suggests that you'll always have some sort of oscillatory feature or non-ODE type feature in our solution. So this seems to be a fairly reasonable expectation. Okay, and just to finish off with these K greater than 0 fluids, I mentioned that we can sort of approximate when a shock first forms. So here I'm plotting the shock time. So this is the first time I think a shock is formed in my solution based on some sort of norm quantity. And what we see is it scales roughly exponentially with the size of my perturbation. So if I take a larger perturbation, the shock forms quicker, which is sort of heuristically what you'd expect. Now the question is, why does it have this particular sort of exponential scaling? So while I don't have a strong idea of exactly why it has an exponential scaling, one idea is that this is essentially plotting when sort of the maximal time of existence from local well-posedness breaks down. So in a sense, we're plotting, when does local well-posedness fail in some sense. And of course, there we expect some sort of, exponential bound. Our solution should be bounded by some exponential quantity times the initial data or the norm of the initial data. So maybe this is why it has some sort of exponential scaling, or it could be totally unrelated. I'm not sure yet. I think it definitely needs a little bit more work to understand the exact scaling here. Okay, so that was for barotropic fluids. There we always observe these oscillatory shocks and the metric variables appear to be more or less smooth but oscillatory. At k equals 0, which is this dust case, we get a very different type of behavior. In particular, we observe that we form these stationary shocks in the fluid variable, so we don't have this oscillation anymore. We observe sharp features which are similar or seemingly discontinuous in the metric variables. And in particular, this totally contrasts the fixed background results. So their fluids are stable on this fixed background. Okay, so to make these claims a little bit clear, let's look at some animations again. So here I'm plotting the fluid velocity, and what you see is we don't have this sort of rapid side-to-side oscillation. Instead, we have just a single shock forming in our solution. So similarly, I can look at the metric function, and here the behavior isn't particularly oscillatory, but it is quite different. And as you'll see, it looks like we form sharp, seemingly discontinuous features in the solution. So at least to me, that looks very discontinuous. And that's sort of interesting because you shouldn't expect discontinuities in the Einstein part of things. So the Einstein equations are linearly degenerate, so you shouldn't expect, at least to my understanding, you shouldn't expect shocks to form from smooth initial data. And so the question is, well, what is causing this? So I don't have a great idea why the dust case is so different, but I do want to mention a few sort of interesting facts about this case. So the first is that this case is much more difficult to numerically evolve. So in particular, we had to use shock capturing methods for both the fluid and the metric variables. So in the barotropic k greater than 0 case, we use finite difference methods for the metric, but here we're using shock capturing for the metric. In particular, if you do try and use finite difference methods, you get sort of spurious oscillations and the code crashes very quickly. So regardless, it seems, of whether this is a discontinuity or not, it is clearly more difficult to evolve this regime. Additionally, we had to massively reduce the time step, so it's just more computationally intensive to evolve these perturbations. And even then, the numerical scheme is still really struggling to resolve this k equals 0 behavior. But given all this, the question remains, is this a sharp feature or spike, or is it some sort of numerical instability? Either would be interesting. If it is a numerical instability, is the natural question of what about this k equals 0 regime means our methods fail. But let's say, for the sake of argument, it's not a numerical instability and it is some genuine feature. What is that feature potentially? And the only thing to me that comes to mind is it's very reminiscent of these spikes you can see when you approach the initial singularity in these cosmological spacetimes. So here I've got a plot taken from a paper by David Garfinkel, which shows a spike in the metric functions in these Gaudi spacetimes. And I would argue that this is a very similar sort of seemingly discontinuous feature that we see in our solutions. Now, to my understanding, these spikes are a sort of ODE feature. They're caused by these Kasner bounces you get as you approach the initial singularity. Here, we're of course going to the future where I don't think these metric spikes sort of naturally form. So the question is, well, what about this dust case is sort of causing this sharp discontinuous feature? And right now, I'm not sure. So I think hopefully in the future, we will have some good explanation of why this case behaves that way. Yeah, and that's really all I wanted to say today. So to summarize, for these decelerated cases, shocks form in the fluid for all values of k. The k greater than 0 solutions are never ODE dominated. In particular, we never see this Rendall instability that we saw in the accelerated case. And then at k equals 0, we're getting these sharp features in the gravitational variables, and it's not quite clear, what is causing this. Is it a numerical instability, or is it actually some genuine feature of the solution? And then just to conclude, some suggestions for future direction. Obviously, a really natural direction would be to get a rigorous proof of Rendall's instability for Einstein-Euler. Even in the Gaudi symmetric case would be great. So further studies of this k equals 0 case in the decelerated regime are definitely necessary to sort of determine the cause of this spiking behavior. And then the natural sort of generalization of all of this is to ask, well, what happens when you now evolve towards the past? And there you could get, in principle, much more complicated behavior, so mixed master type oscillations and all these sorts of things which may interact with shocks in the fluid. So that's a natural sort of long-term extension of all this work. Yeah, and that's all I wanted to say. Thank you very much.
Thanks, Elliot, for the wonderful talk. Really good talk. So it's time for the question from the audience. So if anybody has any questions, please go ahead and unmute yourself and ask Elliot anything you want to ask. Questions from the audience? Maybe I'll ask some questions. I actually have so many questions to ask, but I won't take a lot of your time earlier. So,
Yeah.
yeah. So this is actually really interesting. So I'm curious, like when you do these numerical simulations, it actually tells you a lot. And how do you solve this? For the Einstein-Euler case, how do you solve the numerically the constraint equations? Do you?
So there are two cases here. So I in the accelerated case, we used a formulation where you actually have to enforce the constraints. So we enforce the Hamiltonian constraint numerically. We choose that as an evolution equation.
Right.
And in the momentum constraint, you check after the fact. So you see how well it's preserved, and you want to show that it's converging to zero, or the constraint violation converges to zero in the limit of your resolution. In this decelerated case, you don't have to enforce the constraints. So the Gaudi model in this particular case totally decouples. So it's an unconstrained model in that case.
Right. Great. And what is the gauge you choose for this? What is the time gauge that you choose for this coupled Einstein-Euler case? Do they depend on this?
In both cases, where the time coordinate is proportional to the area of your symmetry orbits.
Right, because they're expanding, so this is monotonic. I see.
Yeah.
I think you showed this. This is actually pretty interesting. The behavior you showed, the function of shock formation time as the size of the initial data. You said it's like exponential, right? You showed this diagram, which is kind of actually pretty interesting. I remember, like in Christo. I mean, of course, the context was. I mean, he was on the Minkowski. He was not expanding background. He was on Minkowski for the Christodoulou's case, and he was like especially rotational case. So I think there is like he gives some estimate, if I'm not wrong, like gives what the shock promotion time goes like e to the some constant divided by the initial data size with some dimensional. So there is some estimate, I think, for this comes from this energy estimates of nonlinear, like quasi-linear wave equation. I mean,
well,
I'm
that's
wrong, but
good. I hope it's exponential.
yeah, it's exponential. I remember seeing that, like uh, I remember seeing that, and because yeah, this is actually very interesting. This is very interesting. You see that in numerics, and wow. Yeah, in numerical in the numerical simulation, interesting. Do you ever use some kind of like energy, like you mentioned something like entropy function, right? Just which is conserved if you don't have any shock, but if you for high regularity, but if it's low regularity, the entropy actually kind of monotonically increases or something, right?
Yeah.
Yeah, yeah. Is that I don't remember like anybody any analytical study on is that like do you know any analytical study like some mathematical studies on like which kind of takes into account this monotonicity of the entropy function to control like say some control on the solutions.
Yeah. So typically these entropy functions. So this really comes from the sort of background of conservation laws and balance laws and all this sort of thing.
Right.
And,
Yes.
these entropy functions are really, well, they were an attempt to show that you have unique solutions when shocks form.
Right.
So the idea is that the sort of unique admissible solution at a shock is one that satisfies an entropy inequality.
Right.
Now, in general, I think this is not unique. So I think this is known now that you can have multiple solutions which satisfy these entropy inequalities. So in that sense, it's not like the be all end all. But from a numerical point of view, the idea is that you would at least like to converge to something which is in the class of these entropy satisfying solutions. So that's
Right.
why numerically you would want to check the entropy and show that it's, conserved or increasing or something like that.
Right.
Yeah. But it's about uniqueness. That's sort of, I think, the main
Nice.
idea behind them.
This the Feynman's this derivative test, like when you compare these norms of the derivatives and the entropy technique, are they equivalent or kind of different, like in some way?
These norm quantities equivalent, is that?
Yeah, like these two, they're not equivalent, right?
Well, on a practical level, essentially, because they're just some quantity that you specifically look at, and you look at a sequence of solutions and see how that quantity changes. On a mathematical level, I don't think there's any particular connection between the two, to my knowledge, at least. It's just two sort of
Yes.
rough ways of approximating when a shock is forming.
Nice. I won't keep you for long. Yeah, this has been a great talk, and thanks for answering all the questions. Thanks for the great talk. And if anybody else has any questions, like right now, would be a good time to ask Elliot. Or if not, we'll probably stop recording.